Today, I'd like to introduce our project objectives and achievements. Our research focuses on the development of advanced atmospheric simulation models. In realization of weather control, one of the biggest challenges is how to assess the controllability and determine the optimal intervention method for individual target phenomena that could cause serious damage to society. As Mia-san pointed out, the chaotic nature of the atmosphere is strongly related to the controllability. Even small variation in initial atmospheric conditions could lead vastly different weather outcomes. One important aspect of controllability is understanding this inherent uncertainty in atmospheric phenomena. A wider range of potential outcomes of future states offered the opportunities for modification, although it introduces a greater uncertainty, making prediction more difficult. Accurately quantifying this range is crucial for better informed decisions about the better interventions. For example, if the heavy precipitation is likely to occur in the specific location, meaning that there is a small range of possibilities, it may be more effective to modify other properties like intensity or timing of the event rather than modifying the location to mitigate the damage. But if our estimates of the range of possibility of such quantities are inaccurate, we may fail to modify the weather. Or worse, they cause even greater damage. So the accurate estimation of probability distribution for future state is essential for weather control. Our primary objective is to create a new generation atmospheric simulation model that can accurately estimate these probability distributions. By focusing on innovating the simulation model, we aim to contribute to more reliable disaster preparedness strategies. To achieve our goals, we focus on the three main research areas. The first, we are developing the sub-meter scale simulations, which allows us to capture more detailed atmospheric phenomena, thereby reducing the errors and improving model accuracy. It consists of the development of the surface turbulence scheme and higher accurately the dynamical core. The second, we are developing the physics-based process schemes to incorporate the real-world physical phenomena into our model, enhancing the model reliability. It includes the development of the particle-based cloud microphysics schemes and the aerosol cloud precipitation and lightning integration scheme. It ensures that our model can not only mirror what is actually happening in that atmosphere, but also accurately simulate the effects of artificial interventions. Lastly, we investigate the advanced evaluation methodologies to evaluate the effectiveness of our model and continuously refine it. Throughout our research, we have made significant progress. And let me introduce a few examples. The first, we have developed a novel cloud scheme. As you know, the clouds consist of tiny cloud particles. But in traditional simulations, the clouds are treated as continuous statistical quantities, which lead to loss of information and errors. And also, it requires lots of assumptions and hyperparameters. In our new cloud scheme, we represent the actual cloud particles as particle in simulations, which allows for more realistic cloud simulations. These are the simulation results of observed cumulonimbus clouds. This figure shows the vertical profiles of the number of liquid water droplets. It is known that in real cumulonimbus clouds, the liquid water can exist at the altitude where the temperature is about minus 40 degrees Celsius. The traditional simulations shows no liquid water particles at such a low temperature altitudes. On the other hand, our scheme successfully captures them because of the more realistic representation of physical processes, microphysical processes. The accurate representing the supercooled droplets are essential for the cloud seeding, as the presence of the supercooled droplets directly influences on the effectiveness of the seeding interventions. So our scheme potentially enhances the ability of the evaluation of the effectiveness of the cloud seeding. The second example is surface turbulent scheme, which calculates the vertical transport of momentum, energy, and moisture from the surface to the atmosphere. The surface turbulent transport plays a significant role in the atmospheric phenomena, as most of energy in atmospheric motion and moisture are supplied from the surface. In conventional turbulent scheme, the transports are calculated based on assumption of horizontally and temporary homogeneity, which is reasonable in lower resolution simulations. Our new turbulent scheme removes this assumption because it is no longer valid in ultra-high resolution simulations, such as sub-meter scale simulations, which we aim to realize by 2050s. This diagram shows the vertical profiles of the near-surface momentum transport in simulations and observations, demonstrating that the advantage of our scheme over conventional one, as shown around here. The accurate surface turbulent calculations is crucial for weather control, as most of intervention would be carried out at the surface, and their effects must be accurately transferred into the atmosphere in simulations. This makes our new scheme critical advancement for weather control. In conclusion, our project represents the significant step forward in weather control technologies. Now we are evaluating the effectiveness of our new model in terms of the probability distribution estimation. It is important to note that even our model is not perfect and requires the continuous development for further improvements. And finally, I'd like to comment on the AI-based simulation. Nowadays, as you know, the accuracy and the reliability of these data-driven simulations has been significantly improving. And it is reported that some of them outperforms those of physics-based simulations. So there is no doubt about their usefulness in a wide range of contexts. However, in the context of weather control, the physics-based simulations still play a significant role. We have limited real-world experiences on the, extreme weather, especially under a changing climate. Moreover, we have almost no data on controlled severe weather with interventions. Therefore, I believe that the simulations based on physical laws alone can produce a reliable prediction for such uncharted weather. And continued development of the physics-based simulations significantly will contribute to the weather control and then the safety of society. Thank you for attention.